We have y equals tan squared x drawn, along with y equals 4 cos 2x minus 1. And we're asked to show the area of the finite region, that's the shaded region, between these two curves in the interval from minus pi over 2 to pi over 2 is given by this. So this is going to be an integration, and we can immediately write that down actually. Of 4 cos 2x minus 1. That would give me, and it's going to be up to the points where they intersect, minus tan squared x dx. Between, we don't know these points, which is going to be the tricky bit of this question. Let's just call them A and B for now. But at least we've set up what we need to do. Integrate underneath this curve between A and B, which will give the whole area, and then subtract the small area from tan squared. Now actually, there's an even better way we can do it, because this is symmetrical. Tan squared is symmetrical, and 4 cos 2x minus 1 is symmetrical. So what I'm going to do is I'm just going to work out this blue area, and then I'm going to double it. So in fact, I can change this a to a 0, and then just double the integral. That's a really nice technique that not always talked about much in A level, but if you're doing these sorts of questions, you want to make your life as easy as possible and just substitute in one limit, and then it's substituting in zeros generally, you know, much more simple than substituting in other non-zero numbers. So the question is, how do we get B? And it will occur when the curves intersect. So when tan squared x is equal to 4 cos 2x minus 1. So I've got a trig equation to solve. At the moment, I've got tan squared and I've got cos 2x. That's not a great place to be, so I'm going to need to use some identities to improve the situation. And sometimes you've got to play around with this. So I'm going to write tan squared as sine squared x over cos squared x. And then I've got to think about how I deal with cos 2x. Well, cos 2x is cos squared minus sine squared, which I can rearrange to 2 cos squared minus 1, or 1 minus 2 sine squared. I don't want to use this top one because I don't want an equation involving sine and cos. So I'm going to use the second one because then I can get the right hand side all in terms of cos, and at a later point I can change sine squared to 1 minus cos squared. I think I could do this exactly the same for sine squared. I've just chosen to go this route. So it's going to be 4 and then 2 cos squared x minus 1. Just got to remember that I'm also still minusing 1 from that. Let's simplify this, but I'm not going to rush it, so I'm going to sort the right-hand side out. I'm going to get 8 cos squared x. Then it's going to be minus 4 minus 1. So I've got minus 5. So sine squared x will equal 8 cos to the 4x minus 5 cos squared x. And I can replace sine squared x by 1 minus cos squared x. Therefore, we'll get 8 cos to the 4x minus 4 cos squared x minus 1 is equal to 0. Now you can try and factorize this. You could try 8x and x, but you're not going to get a minus 4. You could try 4 and 2. You're not going to get a minus 4. This isn't going to factorize. By the way, what I didn't say is that this is a hidden quadratic in terms of cos squared x, but you might have already spotted that. So it must be that cos squared x, we can use the quadratic formula, and it's going to be 4 plus or minus minus 4 squared minus 4 times 8 times minus 1, so it'd be plus 32 here, all over 16. And I know that doesn't look very nice, but we got to roll with it. This is correct. This here is root 48, which is actually going to be 16 times 3 in here, so this will be 4 root 3. And if I write it like this, I can cancel out the 4's. So that 4 will cancel out with this one and this one. So I'll get 1 plus or minus root 3 over 4. And I'm going to reject the negative because it's cos squared. We really wanted x, didn't we? But we're just going to have to cope with it being um, in terms of an inverse cos function. B is going to be inverse. Sorry, I've rushed it, haven't I? Because I haven't even said what cos x is yet. So cos x will equal plus or minus the square root of 1 plus root 3 over 4. And b, remember, was a positive value between 0 and pi over 2. So it's going to be inverse cos of the positive one. And this looks horrendous as a limit, but remember we still have to integrate some trig functions and look at the final answer. There's roots within roots, so it's, this is actually going to be okay. Let's bring it together then. And if you struggle to get this limit, then you can still, of course, perform the integral, and it just be the limit that causes problems. So r was equal to 2 times, remember, the integral from 0 to b. I'm just going to leave it as b for the moment rather than write this out every single time. 4 cos 2x minus 1 minus tan squared x. I could write it as 2 separate integrals if I need to. Sometimes that can be good because you might need to do integration by parts on one integral and so on. But let's deal with it and see what happens. So if I integrate cos 2x, I'm going to get sine 2x, but a half sine 2x. So this will become 2 sine 2x. Of course, you can differentiate back to check it. Then we would times by the 2 to get 4, and sine would become cos. So that's okay. Then I'm going to be minusing x. All right, we've got to think about how we integrate tan squared x. And this is going to be more identities. So sine squared plus cos squared is 1. Divide through by cos squared, so we get tan squared plus 1 is equal to sec squared. And that means that tan squared is identical to sec squared minus 1. And to be fair, I probably should have done that before I even integrated, but it was only when I started looking at it I thought, okay, and now I need to mess with this. So it's going to become, all right, so I'm just going to I will separate it into 2 integrals. So I've got this part, and then I'm going to be integrating from 0 to b, but it will be sec squared x minus 1. But this is good, and this is your classic identity. This is how you deal with integrating tan squared, because when you integrate, because the derivative of tan x is sec squared x. That's one worth knowing. So I'm going to get 2 sine 2x minus x minus tan x, and this will become plus 1, which I integrate, which will become plus x. And these cancel. I could have actually, if I'd done it right up here, I wouldn't have even needed to have integrated it. Okay, we're nearly there actually. So we just need to put it together. Um, right, it's going to be, I'm going to bring that 2 back in. So it's going to be 4 sine 2x minus 2 tan x. And I am evaluating between, it was inverse cos of 1 plus root 3 over 4 square rooted. So how to go about dealing with this? Um, I don't want sine and I don't want tan. I want everything in terms of cos, really. I can write this. Sorry, didn't want that. I want to write that sine 2x is equal to 2 sine x cos x. So I'll get 8 cos x. Now I need to deal with the sine x. I want it, so forgot to put 0 there. I want it so that I can put inverse cos in, finding sine of inverse cos. This is how you do it. We know that sine squared is 1 minus cos squared, and therefore sine is the square root of 1 minus cos squared. So it's going to be 8 cos x multiplied by 1 minus cos squared x. That's my sine x. And then I'm going to minus 2 sine over cos. So it's going to be 1 minus cos squared x, because that's again sine x divided by cos x. Okay, and I'm evaluating again between this limit inverse cos and 0. I can't fit it all in. We're ready to finish this off. So I'm going to get 8. Cos of inverse cos is just going to cancel, so it's going to be 8 lots of this square root. So it didn't matter that I had my limit in terms of inverse cos because it's cancelling out. And then inside this square root, I'm going to get 1 minus cos squared x. So it's going to be this, because I'm going to be squaring the square root of 1 plus root 3 over 4. So I've dealt with that part. Now I've just got this other part. I wonder if I can fit it in. It's going to be 2 lots of, and then it's the same thing again, square root of 1 minus 1 plus root 3 over 4 all over the square root of 1 plus root 3 over 4. Okay, and we might not quite have the answer, but at least we have an answer all in terms of surds. And what we're trying to get to is this here. So we just got to try and cancel it down. I can write this as 8 root 1 plus root 3 over root 4, which is just 2. Here it's going to be 4 minus 1 minus root 3 over 4 when I put it over a common denominator. And then the same over here, minus 2 lots of 4 minus 1 minus root 3 over 4 all over 1 plus root 3 over 2. This and this will partially cancel to give me 4. So 4 root 1 plus root 3. Then we've got 3 minus root 3 square rooted all over 2. So that will cancel with that partially. And then minus 2 lots of 3 minus root 3 over 2 all over 1 plus root 3 over 2. These will cancel. Alternatively, you can times by the reciprocal of this, and then you can see it that it cancels. We're getting there. Let's keep going. I can see that I've got a 2 outside the third. I think this is going to be this one. So I'm going to need to bring it under one single root. I might just do a little line to kind of put some things together. 1 plus root 3 times 3 minus root 3, all in a root, minus 2 lots. Okay, hopefully this is going to become this. 2 lots of root 3 minus root 3 over root 1 plus root 3. I've got a little bit more to do with that second term. Let's deal with the first term. So I'm going to get 3 minus root 3 plus 3 root 3 minus 3. They cancel. And over here, okay, I'm going to put it in one big root. And then I think I can rationalize the denominator. But next line, let's just continue to tidy it. I'm going to get 2 root 3 here. So smiley face for this first term. And then it's going to be 3 minus root 3, and I'm going to times by root 3 minus 1 all over root 3 plus 1 times root 3 minus 1. Of course, I could have times by 1 minus root 3, but that would have been a negative, so this was just a bit easy to deal with. Then I'm going to get 3 root 3 minus 3 minus 3 again, and then plus root 3 all over 3 minus 1. I'm going to get, just look at the answer, I want 4 root 3 minus 6 all over 2. And finally, I can just divide through by 2. Whew, we are there. Both terms looking good. Lots of stuff going on in this question, but we've managed to find the area. And yes, it's kind of complicated, but isn't it amazing that we can actually find that exact value without a calculator between these two curves.